Exponent rules. The power of a quotient rule. Our next rule is for a quotient, also known as a fraction of different bases, to a power. We will take the outside exponent and apply it to the numerator and to the denominator, making two small problems instead of one large problem. For our next example, 2/3 to the 4th power. So we will take the 4 with the numerator and with the denominator. This will give us 2 to the 4th over 3 to the 4th, and then we would work those out. 2 to the 4th is 4 copies of the 2 is 16. 3 to the 4th, 4 copies of the 3, is 81. This will give us the same answer, but in a shorter form than making 4 copies of the entire fraction. For our third example, 2x to the 5th over y to the 4th, the entire fraction to the 3rd power. We will apply the 3 to the numerator and denominator, making 2 problems instead of one large problem. And then we'll apply it to the denominator. On the numerator, you're now back into one of our other exponent rules, which is a product to a power. So you're going to take the 3 to each piece. This will give us 2 to the 3rd times x to the 5th to the 3rd. We can work those out. 2 to the 3rd is 8. X to the 5th to the 3rd. We'll keep the base and multiply. And for our denominator, a power to a power, we can go ahead and work that out. Keep the base and multiply. Exponent rules. The quotient rule, also known as like bases as a fraction. For this problem, we're going to try to figure out the rule when we have like bases as a fraction or a quotient. So we'll write it out. X to the 7th means that we have 7 x's. 1, 2, 3, 4, 5, 6, 7 on the numerator. And x squared means that we have 2 x's on the denominator. When you have products, you're allowed to divide out common factors. So we are able to match up and divide out these 2 x's. Now let's see what we have. Total, we have 5 x's, or x to the 5th in the numerator, nothing in the denominator, but we were really dividing, so the denominator is a 1. You don't have to show a 1 in the denominator. So what could we do just with the 7 and 2 to get the 5? We subtract. So dividing these factors out, we can subtract them off, or subtract the exponents. So for example 2, we have a direct application of the rule. Like bases as a quotient or fraction, we will keep the base and subtract the exponents. 10 minus 2 is 8. Example 3 looks like a much more difficult problem, but it is really just 3 small problems put together. We have numbers, we have x's, and we have y's. For your numbers, you will just reduce like a normal fraction. These have a common factor of 3, so we can divide by 3. 3 into 3 goes 1 time, and 3 into 6 will go 2 times. For your x's, you have a fraction. Keep the base and subtract. You have x squared. For the y's, keep the base and subtract. Don't forget, this one has a 1 if you don't see an exponent. So 5 minus 1 will give us 4y's, or y to the 4th. And then you would want to recognize this also without the 1 in the numerator. It's okay to have it on there, but a simpler form would leave it off, because 1 times x squared y to the 4th would just give you x squared y to the 4th. So you don't have to have the 1. Exponent rules. A zero exponent. Our next rule, x to the 0 equals 1, is really a definition. A definition is made anytime there is something in a gray area. Let's recall what 2 to the 3rd means. It means to take 3 copies of the base. So nice, concrete meaning, and then you could work it out. But if we tried to have a 0 for an exponent, how do we make 0 copies of something? So we have something that's a little gray. Let's see where this might come from. Let's think back to some old problems for a moment and to see maybe why this definition of x to the 0 is equal to 1. First of all, let's think about 3 divided by 3. I think we all would agree that is equal to 1. Anything divided by itself goes 1 time. And how about x to the 5th divided by x to the 5th? This is also going to be 1. We could write it out. But we are dividing, and everything divides out and it goes 1 time. Now, if we tried our previous exponent rule of like bases as a fraction or a quotient, the rule was keep the base and subtract the exponents. And so this is where this new piece is showing up, this x to the 0. So we want that to be defined as the real answer to this problem, which we know is 1. So this is kind of where this definition comes from. This is a situation where it shows up by 5 minus 5 gives us the 0, but we know this is equal to 1. Now, this was just to help you understand. What you have to know is how to apply this definition. We will use our definition to help us simplify these two problems. What you want to notice is, what is the 0 really with? In the first situation, the 0 only applies to the x. So this piece of it, the x to the 0, is 1, but you still have it multiplied by 3. So our answer there is 3 times 1 is 3. For our second situation, the 0 is beside the parentheses, so the 0 applies to the entire piece. This one is equal to 1. It doesn't matter what's inside, the entire piece is to the 0 power, so that is a straight application of your definition. Let's look at this example. Simplify negative 5x to the 0. So we want to know, what is the 0 really with? It is only with the x, so that piece of it is equal to 1 by definition, times the negative 5 will give us negative 5. This last example is often used as a type of trick question, It looks really hard. That's very complicated on the inside. But what you want to notice is the 0 is beside the parentheses, so it applies to the entire thing. So by definition, this is equal to 1. You really don't have to do anything. It is something to the 0 power, so it is equal to 1. Exponent rules. We'll summarize our exponent rules. Our first exponent rule was when we have like bases multiplied, and our rule is to keep the base and add the exponents. Our next rule we had was a power raised to a power, and we will keep the base and multiply on the exponents. Our third rule was if we have a product to a power, we take that outside exponent down to each piece of the product to give us a to the m, b to the m. Our fourth rule was a fraction of different bases to a power, or a quotient to a power. And we will take the outside exponent with the numerator and with the denominator to make two small problems instead of one large problem. Our fifth rule was a fraction of like bases, or a quotient of like bases. And we're going to keep the base and subtract on the exponents. Our sixth rule was a definition. X to the 0 power, or anything to the 0 power, is equal to 1.